So over the last few years, I have prepared for and appeared in multiple system design interviews. And one of the things that I've learned in these interviews is that interviews aren't looking for the most complicated architecture. They are looking for how you actually think. So are you asking the right questions? Are you identifying the bottlenecks? And are you evolving your design instead of over-engineering it? So in this video, I'll walk you through on how I would answer one of the most common system design interview question, design WhatsApp. So we'll begin with the requirement gathering and gradually building a production ready architecture, discuss on why every component exists, look at their alternatives, like wherever applicable, and finally answer some of the trade-off questions that interviews commonly ask. So let's not waste any more time and begin with so whenever I'm asked to design any system, I never start drawing immediately. First spend a couple of minutes understanding the requirements because the architecture depends entirely on what we are trying to build. So let's start with the functional requirements first. So I'm going to write functional requirements. The first one will be obviously one-to-one messaging. Okay. The second one will be group messaging. Third one will be the message should be real time and the delivery as well. Okay, the spellings are right. Then we need to share the media as well, media share, and then we have obviously we forgot about the read receipts. User should know that their messages have been read. Then we will have the typing indicators. Okay. Then we will also talk about online and offline status of user. Okay, and then push notifications because notifications are very important. Then the last but not the least, multi-device synchronization, because you can open your account in different devices, right? Like your laptops or your phone or your tablets, right? So this is our synchronization. So these are our functional requirements. I'll move them here. Now let's talk about our non-functional requirements. Non-functional requirements. Okay. So we need the high availability, right? So high availability. Reason being, user expects messages to be working all the time, right? Message should be delivered with very precise moment of time, like very low latency as well. Okay, so that would be our availability. So that would be our second non-functional requirement, which is low latency, because we don't want that I send a message and it get delivered after like 10 minutes or 5 minutes, right? Well, that's a very large amount of time, but yeah, we talk about milliseconds here, so low latency. Now next is the system should scale horizontally as the number of user grows. So scaling, and it should be horizontal. Okay. Next we will be talking about the fault tolerance, because single server failure shouldn't affect the entire application, right? So fault tolerance is another non-functional requirement that we will take care of. Then I'd say that consistency is very, very important here. Okay, and message requires strong consistency because ordering is very important. Like let's suppose I send hi, then how are you, and then my name is Prajwal. If it get received as my name is Prajwal, how are you, and then hi, it's not a good sign for your application, right? So consistency is also very much important. Now these are my non-functional requirements. Now let's talk about one more critical aspect of our system design interviews, which a lot of people miss and is actually very important. That will be our capacity estimation. Okay. Now what is the capacity estimation? So it is the data on which your design will actually work on, like your app will work on. So it will be number of users, and as we talk about the WhatsApp, there will be users, there will be their messages. So messages can include text, videos, and images. So we need to keep track of how much capacity are we going to serve with our with our application, and while keeping that in mind, we'll design our entire system. So let's suppose you have 100 million daily active users, and each user is for now sending 20 messages. Okay, so it will come out to be 2 billion messages. 86400 divided by 86400, which will be approximately, I'll say, 24k or 23k messages per second. That's a huge count. Now peak traffic is usually much higher, so I design something that will serve around 2 lakhs to, let's say, 3 lakhs messages per second. Okay, now these many messages result in a lot of requirement in the storage, so it is something else to be considered. Now even if each message take around like 1 kilobyte including the metadata, we are already generating terabytes of new data every day. Media like images and videos will push storage requirements into petabytes. Okay, so I'll just say storage requirements around petabytes. Okay, so this immediately tells me exactly how we will be reading our system. So eventually we'll be requiring a distributed systems, right? Now that we understand the problem, let's actually start building the architecture. Okay, I'll move it here and keep it like this. Okay, now I always prefer starting with the simplest possible solution and then improving it only when I identify bottlenecks. That's exactly how I'd approach in a real interview as well. Okay, so let's start off with the basic architecture. I'll start with the components like user, load balancer, your server and your database. Server and database. Okay, I'll keep them here. I'll connect them, and voila. So this is our basic architecture. Now let's understand how this will work. Now whenever user A sends the message, the request first reaches to the load balancer. Then the load balancer forwards the request to our servers, and servers performs entire business logic and then stores the messages in the database, and finally returns a success response back to the user. So over here, right? At this point, we have built a very simple messaging application. For this, you have to literally refresh your screen again and again to check if the messages have arrived. Okay. Now, interviewer might come and ask you, why did you introduce a load balancer right from the beginning? Okay, because you said it's a basic architecture, but why from the beginning? Now, without a load balancer, every request would hit a single server. That server has limited CPU, memory and network bandwidth. As traffic grows, it will eventually become an overload, and more importantly, it becomes a single point of failure. So if that server crashes, the entire application will go down. A load balancer distributes the incoming request across the multiple servers, improving both scalability. Now, at first glance, this architecture seems complete. User can send messages are stored, everything looks fine. But there's a major problem. Imagine I send you a message, and how does your phone know that I have sent you something? Using your current architecture, your application would have to repeatedly ask the server, do you have a new message? Do I have a new message? Or this becomes very hectic. Okay, so this technique is called polling. Polling is very simple but extremely inefficient. Imagine 100 million users asking the servers every 2 seconds that whether they have received any new messages or not. Even if nobody sends a single message, the servers still have to process millions of unnecessary requests. That's a huge waste of CPU, bandwidth and the infrastructure. Okay. Now, instead of making the client repeatedly ask the server for new messages, I'd rather let the server notify the client the moment a new message arrives. Okay, so for this, we'll introduce chat servers. So unlike our application server that was already existing with us, I'll rename it to server application. So unlike a normal application server whose job is to process HTTP requests, the chat server is responsible for maintaining long-lived connections with every connected user. So my server application will come here and my chat servers will come here. Now for this, there's one more thing that we need to make sure about, that this chat server only comes in process, only comes in action when there is a request for if a request from the user if I have received a new message or not. Okay, so basically so this will connect with our database as well. Okay, and I'll mention activates only for notify recipient event. Okay, so this is how I describe my chat server. Now for this, your interviewer might ask you some questions regarding this. Okay, so they can go ahead and say why a separate chat server, why not in the existing application server. So for that you can go ahead and ask say that traditional application servers are optimized for short-lived HTTP requests. A request comes in, the server sees it, the server processes it, and then it returns a response, right? And the connection closes. Chat servers behave very differently. A user opens WhatsApp in the morning, and the connection may remain active for several hours. Managing millions of persistent connection requires a different strategy, a different scaling strategy. So by separating chat servers from the application servers, we can independently scale both the components. If message traffic increases, I only scale the chat servers. But if the API traffic increases, I scale the application servers. This separation also keeps each service focused on a single responsibility, which is a very huge win. Now, the communication between the client and the chat servers happens over the WebSockets. Now, what are the WebSockets, right? So, HTTP follows a request response model, right? The client sends a request, the server responds, and the connection is typically closed. But if the server wants to send another message later on, it can't. The client must send another request first, right? A WebSocket works differently, right? It establishes a complete persistence and a full duplex connection between the client and the server. Now, once the connection is established, both the sides can send data without any interruption and whenever they want. Okay, so this avoids the need of creating a new connection each time anyone wants to send a message. That's exactly what messaging applications need. The moment I send you a message, the chat server can immediately push that message to your device. That's it. Now, at this point, our messaging application supports real-time communication, right? But as the traffic increases, another bottleneck starts to appear. Every message requires fetching user information, active sessions, and conversation details from the database. Continuously hitting the database for frequently accessed information isn't scalable. So the next component, iDash, will come over here. Now I have removed the database. I shouldn't have done that, but yeah, we can add it again. So this is our cache and this is our database. So our server application will hit the cache and that will hit to the database. The chat server can do the same. Okay. Now what happens is, instead of asking the database every time, the server first checks the cache, and if the data exists in the cache, we immediately return it. Otherwise, we fetch it from the database and then store it in our cache, and that cache can be used for a future request. Okay. Now your interview can go ahead and ask you why Redis. Okay, so for that you can answer like there is also an option of memcache, but Redis is one of the most popular in-memory databases, and since everything is stored in RAM instead of disk, read and write happen in microseconds instead of milliseconds. That's exactly what we want from the frequently accessed. Now I'll handle over here like this. Okay, I'll use Redis. Now there's one more thing that comes up in the mind. So sometimes interview, like one time I said, like I read it somewhere and I said it, that Redis supports richer data structure. I read it somewhere, and my interviewer asked me this same question. I mentioned that Redis supports richer data structures. What exactly does that mean? So obviously I read about it, I did some research, so I gave the answer for that. That memcache primarily stores simple key value pairs, but Redis on the other hand supports multiple data structure. For example, strings, they can be used for user status, then hashes for user profile, then sets for storing group members, and then list to maintain the list of conversation. So sorted sets are also useful, And since messaging applications naturally work with a collection of groups, conversations, and online user, so Redis makes it more easier. So by richer data structure, I means that it provides capability with compatibility with lot of data structure, and we can store different type of values in our cache. So this is what I meant with the richer data structure, and my interviewer was quite simple. Now our reads have become very much faster, but writing messages still introduces another challenge, right? Now suppose user A sends a message to user B. After storing the message, several other things needs to happen. We need to deliver the message, we need to notify all the users, all the user B's devices. Then we need to send the push notification if user B is offline. Then we need to update the analytics, we need to update the search index, and we need to store the message backup if required, right? If our application server performs all these actions synchronously, before responding to user A, the user will experience unnecessary delays, which is not good for our application. So instead, I'd introduce a queue. Now, over here, I'll just introduce a queue and a list of workers. Okay, so from our application server, we'll hit the queue, and then they will hit the. So it's basically the cluster of workers instead of just one worker. Okay, worker pool, I'll say. Okay, now for now, let's keep it like this. So think of like is queue is waiting in line of a ticket counter. Okay, whenever the application server finishes storing a message, instead of doing every remaining task itself, it simply places a small event inside of the queue. Okay, for example, user is sent message, let's say hi, how are you, to user B. Once the event enters the queue, the application server immediately responds to the sender that your message is delivered or something like that. Okay. Meanwhile, worker services continuously listen to the queue. Whenever a new event comes in to the queue, worker picks it up and start processing it. Right. Now, your interview can go ahead and ask you why not directly call the worker. So directly calling a worker tightly couples both the services. If the worker crashes or becomes overloaded, the application server also gets affected. A queue decouples producers from consumers. The producer only knows how to publish events. It doesn't care which worker processes it or when it processes it. Okay. Now what happens if the worker crashes? So that's the one of the biggest advantages of using a queue. The message remains inside the queue until it receives a successful acknowledgement from the worker. If one worker crashes while processing the task, another worker can simply pick it up and continue processing. This significantly improves the reliability, which we actually want from our system. Now, interview can also ask which queue would you choose. Is it RabbitMQ or Kafka? Now there are multiple choices like RabbitMQ, Kafka, and some cloud management services like Amazon SQS. Now RabbitMQ works extremely well for traditional task queues. Kafka is designed for very high throughput event streaming, such as our messaging app. Now, since we are building a messaging application, it is expected to process hundreds or let's say thousands of messages every second. Like if we see our capacity, it can serve up to 2 lakhs as well. Okay, so I'd prefer Kafka because it scales exceptionally well if we compare it to RabbitMQ. Okay, now coming back to our system design. Now the worker. Now let's talk about the workers. Workers continuously consumes event from our queue, which is Kafka queue. Okay. Now different workers can different responsibilities. One worker delivers messages, another sends push notification, another updates the search index, another processes media, and so on. Okay. This keeps our application server lightweight while allowing every background task to scale. Correct? So now we are done with everything. At this point we have solved efficient reads using cache and asynchronous processing using Kafka and workers. However, we are still using still under the assumption that we are using the text messages. Okay, let's remove this notify. Okay, we are still using the text message. What happens if we are introducing images or videos? In that scenario, we'll consider it as another bottleneck for our database. And this is our next challenge on how we are going to store these. Okay, So images and videos are fundamentally different type of messages, and they are very different from text messages. Storing, they come in the binary files, right? Storing large binary files inside our database would dramatically increase storage costs, slow down the backups, and negatively impact our database performance. So instead, I'll introduce blob storage. Okay, now I'll introduce the blob storage. What blob storage will do, it will upload image, videos, and the files, the text documents files. The database only stores the metadata like URL, size, and who is the owner of that particular file, video, or image. Okay. Now, your interviewer can go ahead and ask you why not store directly in the database. So you just go and directly say that database are optimized for structured data and queries. Blob storage is optimized for storing massive binary object efficiently. Separating the two allows each system to individually scale and do what they're actually designed for. Now, this application server will also connect with our blob storage. Next comes in the another task. Like, let's say millions of users are forwarding the same viral image. To reduce the latency, what should you do? If your request goes to the blob storage every time, it will become an overload, and it will become a single point of failure. So to reduce this latency and offload the traffic, I place a CDN in between the server and the blob storage. So basically, I'll keep a CDN over here, and not in between the server, but in between the user and the blob storage. This server will automatically, obviously going to the blob storage, yes, but yeah, the CDN will be between user and the blob storage. Now let's talk about searching the messages. Searching directly inside the primary database doesn't really scale well. So instead, I had introduced a dedicated search index. So I will have this search index. Okay. So this search index will have its own replicas as well. Okay. What's its task will be? It's simple. It will be doing the message search. It will be doing the user search, and it will be doing the group searches. Okay. Sorry. Okay. And yes, it will be connected to our application servers. Let's introduce a replica for this. Search index. Okay, and this will be our Elasticsearch cluster, because Elasticsearch provides a very efficient searching. Okay, now I will do it like Elasticsearch cluster. Okay, takes a lot of space, so I'll move it over here. Now a new question can arise, like how does search index work? So search engines like Elasticsearch don't scan every document whenever you search. Okay, instead they build something called inverted index. Suppose we have three messages. Let's say hello Prajwal, good morning Prajwal, and let's say good night. Okay, instead of storing documents first, the search engine stores words as a keys. Right now, hello Prajwal to document 1 and 2, good morning Prajwal will point to the document 1 and 3, and good night will point to document 3. Okay, now this searching of, let's say, Prajwal becomes almost instantaneous, because the engine already knows exactly which document contains that particular word. Okay, now there's one more question that can come. Can we make searching even faster? Absolutely. We can shard the search index across multiple nodes. We can cache the popular searches, popular search queries. We can build efficient indexing only on the searchable fields. And for autocomplete, we can even use a trie data structure to efficiently find words sharing the same prefix. Okay. Now, finally, let's discuss about our database. I generally avoid using the single database for everything, because if we are making it used for everything, it will become a single point of failure. Now, workloads have different requirements such as user, messages, and so on. Okay, so user profile requires transactional and relational data, right? Making SQL databases a really good fit. And message involves extremely high write throughput and horizontal scaling, making distributed databases like Cassandra an attractive option as well. Okay, so search has already been separated into Elasticsearch, so we don't have to worry about it. Media is handled by Blob Storage. So this approach, known as polyglot persistence, where we can choose the best storage technology for each workload instead of forcing every problem into a single database. Okay. Now at this point our architecture is becoming production ready. Okay, but our database still has one major limitation. Eventually one database server won't be enough. So next we'll look at sharding, replication, and rate limiting, and how we'd split the application into multiple microservices. So first I'll introduce another database. Okay, this database will be for our users, and this database will be for our messaging. Okay. So these are our primary databases only. I'll just mention it over here that it will be a Cassandra database. Okay. Now we have our database separate. So just a simple scenario here, right? Imagine we have billions of users sending billions of messages every day. Eventually one database server simply won't have enough CPU RAM or storage to handle that amount of data. One obvious solution is to buy a bigger server, obviously, but that's called vertical scaling, and there's a limit to that. Okay, there's a limit to how powerful a machine can become. So instead, let's do the horizontal scale using the sharding. Okay, now this is our database. Okay, we'll just use multiple instances. Okay, and these will be this will simply mean splitting our databases across multiple database servers. So instead of storing every message inside one database, we distribute them across multiple databases. Okay, so for users I might have had a lot of databases, but obviously for our messaging app we will have different replicas. Okay, so this is our primary database, and these will be our secondary databases. So yeah, now the question comes up, how would you decide which shard stores a message? The shard key is one of the most important design decisions. Since this is a messaging application, I had shard using the conversation IDs. That means all messages belonging to the same conversation will always be stored on the same shard. This gives us two advantages. First, retrieving an entire conversation becomes very efficient because all the messages are stored together. Second, maintaining message ordering, because as I said earlier, like if we receive messages, my name is Prajwal, how are you, and hi, this will be very confusing. So the message ordering is very easier when we use a conversation ID as a shard. Okay, shard key. Now second question will come up, why not use user ID as a shard? That's certainly another option. However, conversation usually involve multiple users, not just a single user, right? If it is a group, it involves more than 2 users. If it's one-on-one, it's 2 users, right? If we shard using user ID, message from the same conversation could end up scattered across multiple shards. Retrieving chat history then requires querying several databases and then combining the result. So sharding by conversation ID keeps related data together and simplifies the reads a lot. Now the last question, what happens if one shard becomes much larger than the other? So this entire thing is called as hot shard. Please specify this word, hot shard. It usually happens when one shard receives significant more traffic than the others. We can solve this using techniques like consistent hashing, virtual nodes, or by periodically rebalancing data across the shards. The goal is to distribute traffic as evenly as possible. Okay. Now, our sharding, obviously we sharded our databases and it improved our scalability. But what happens if one database suddenly crashes? But what happens? So what will happen is we lose access to all the conversations stored on that particular shard. So to improve the availability, I had introduced database replication. Okay, so just like this, we'll call this as same with our user table. We'll call it out as replica. And kind of, yeah, because we copied it, so that's why it became the one change makes it all replica only. So this will be users. Let's check if it is, yeah, it's a primary database, and this will be our replicas. Okay, so now the replication is also done. Each primary database maintains one or more replicas. Whenever the primary receives a write, the replicas are updated as well at the same time. Reads can often be served from replicas, while writes continue going to the primaries only. Okay, now the interviewer will ask, why do we need replication if we are already doing the sharding? Because these two things solve different problems. Sharding distributes the data across multiple machines to improve scalability. Replication copies the same data onto multiple machines to improve the availability and read throughput. In production systems, we almost always use both together. Okay. Now, the another thing that we need to do. So, I would like to introduce a rate limiter. You ask me why. Without rate limiting, malicious user or bots could easily flood our servers with requests. A user could send thousands of messages every second using scripts or anything, which will overwhelm our system. A rate limiter protects the application by controlling how many requests are allowed within a given time window. Okay. Now the rate limiter will come between user and load balancer. So I put it over here. The user request goes to the rate limiter limits it, and then it goes to the load balancer. Now your interview can come up and ask you the question like, which rate limiter algorithm would you actually choose? Now, there are several popular algorithms. The simplest one is the fixed window, where we count the request within the fixed interval, like 1 minute or 5 minutes or 10 minutes. Okay. Now, while simple, it allows burst traffic around that window boundaries. Another operation is sliding window, which stores the timestamp of every request. It's very accurate but consumes more memory. A more optimized approach is the sliding window counter, which approximates the same behavior while reducing the memory usage. Then we have the leaky bucket algorithm. Imagine pouring water into a bucket and that has a small hole at the bottom. Even if requests arrive very quickly, they are processed at a constant rate. Finally, there's the token bucket algorithm. Tokens are generated at a fixed rate. Every request consumes one token. If tokens are available, the request is allowed, otherwise it's rejected. And this, the token bucket is the algorithm that I'll actually use. Reason being, users sometimes send 5-10 messages instantly, right? Token bucket allows burst without allowing the spam. So this is why the token bucket, okay? Now at this point, our architecture has naturally evolved into multiple independent responsibilities, right? Instead of one large application handling everything, I'd separate these responsibilities into individual services. For example, authentication service, user service, message service, media service, search service, and whatnot. Okay. So, uh, so the core services will be mentioned. I would like to mention it here, but I'll put it up first. So these are okay, cool. So as I said, so not the servers, the services. Okay, so these will be our core services. First will be auth. Okay, second will be our user service. Then we can go ahead with conversation messaging. I'll type messaging service. this will be our, as I said earlier, search service will also be there. Okay, and we can add it over here. So application service, auth, messaging, and user. So one more thing that I would like to do is separate these cachings. Okay, let's have chat server its own caching and application server its own caching. Okay, so these are the services. Could have decided better since the start, but yeah, anyways. And this I would say it is a synchronous notify event. So we need to mention that even if it is going to our queue, it is an asynchronous notifying event. Okay. For the cache, we have caching for our application service, which will go to our database. So I'll mention it over here itself. The cache is for our application, and this cache is for our chat. Okay. So I took some time to place these components correctly so it's more visible. Okay. Now how do service communicate with each other? Now there are two common approaches for that. First is for request response communication. I had used either REST API or gRPC. However, for background events like message sent or image uploaded, I prefer asynchronous communication using Kafka only. This allows multiple services to react independently without tightly coupling them all together. Okay. Now at this point we have built a production grade architecture capable of handling millions of users. Now let's discuss some of the follow-up questions that can come up and interviewer can actually ask. Strong consistency or eventual consistency. Now messages require strong consistency because ordering really matters. Features like online presence and type indicators can be tolerated and can be sent as a eventual consistency since minor delays don't affect that user experience. Now next question, how would you guarantee message ordering? So we talked about this earlier, that since conversations are sharded using conversation IDs, all messages within a conversation are handled by the same shard combined with the server side sequence numbers. This ensures messages are delivered in the correct order. Now my favorite question, how would you support multiple devices? So I maintain active device information is inside my Redis cluster. Whenever a new message arrives, the chat server pushes it to active device connected to that particular user. If a device is offline, it receives the message how would you handle offline users? So the messages are stored in the database. If the recipient isn't connected, the chat server won't be able to deliver it immediately. So the notification service will not send a push notification. Once the user comes online, pending messages will be synchronized from the database and then sent to the user. So that's how I approach my designing the WhatsApp question inside a system design interview. And I would like you to also do the stress testing for this particular question. Okay. So in this particular platform, I have the capability to run the simulation. So you can see we have a very good score. The confidence is of 77. Scalability, reliability, fault isolation, latency all are strong. One not way takes the entire system offline. Okay, cool. Traffic spike, we have handled traffic really well. The failure test is also fine. The globalist scaling, edge, delivery, CDN and everything is used. So I think we are good to go. Now the sync load. The sync load is also maintained very efficiently. So let's try to submit our evaluation. So as we saw, the score is 77. We got good points with the services and everything. So yeah, this was our system design for WhatsApp. Now remember, again, interviews aren't looking for the most complicated architectures. They are evaluating how you think, how you identify the bottlenecks, and how you justify every design decision. So if you enjoyed this walkthrough, let me know which system you'd like me to design next. And if you'd like to practice building the architecture yourself, you can do it inside PRISM using the exact same components we discussed today. I'll share the link in the description below. So thanks for watching, and I'll see you in the next video. Thank you.